Any fluid driven by a pump into a series of closed chambers, like your heart pumping fluid into your blood vessels, will flow from areas of high pressure towards areas of lower pressure. The pumping of the heart generates blood flow, and pressure results when flow is opposed by resistance. As long as there is a difference in pressure from one vessel to the next, blood will continue to flow through the system. Here, we can see that pressure continues to decline as we move further and further away from the heart. Pressure is highest in the aorta, slightly lower in the arteries, lower still in the arterioles, and continues to decline as blood moves through the capillaries, venules, veins, and into the vena cava. As the left ventricle contracts, it propels a large volume of blood into the elastic aorta. The aorta stretches because of all the additional volume and pressure. The peak pressure realized in the aorta is referred to as the systolic pressure. It averages about 120 in healthy adults. Because the pressure in the aorta is higher than the pressure in the arteries that are next to it, blood flows from the aorta into those next arteries. During diastole, pressure in the ventricle starts to fall drastically. The pressure in the aorta at this time is represented by our diastolic pressure, which should be somewhere between 70 and 80 in healthy adults. Even though this number is lower than what we saw in systolic pressure, it is higher than what's happening in the ventricle of the heart. To prevent blood from flowing from the aorta back into the ventricle, the aortic semilunar valve slams shut. At the same time, the aorta exerts elastic recoil to squeeze back in on the volume of blood it had accepted from the beating heart, and this helps maintain a sufficiently high pressure to continue being a little bit higher than the arteries that are next to the aorta. So blood moves from the aorta into those next arteries. Aortic pressure fluctuates up and down with the beat of each heart, our systolic pressure and our diastolic pressure being quite different from each other. The mean arterial pressure, MAP, represents the pressure that propels blood towards the tissues. This mean arterial pressure declines as blood moves further and further away from the heart. Smaller arteries are less elastic, and because of that, they exhibit less recoil, so there's not a significant difference between systolic and diastolic pressure in smaller arteries. Because of that, on this graph, we can see right around the time of the arterioles, the difference between systolic and diastolic pressure disappears, and we really only see the line for mean arterial pressure through the rest of the system. Pressure is low at the arterial end of a capillary bed, about 35 millimeters of mercury. It's even lower on the venous end, about 17 millimeters of mercury. This difference is important because it allows blood to continue traveling from the arterial end towards the venous end of a capillary bed, but it's also important that this pressure is so low because capillaries are very thin and fragile, and they could burst if pressure was any higher. Capillaries are permeable, so even a small pressure can cause exchange of material in a capillary bed. On the venous end of a capillary bed, veins have very low pressure. The pressure in a venule is about 15 millimeters of mercury, but since that's lower than the 17 millimeters of mercury we saw in the capillary bed, blood will continue to move from the capillary into the venule. The pressure in a vena cava is about 0. There's so little pressure in a vena cava that it helps continue pulling blood through the system. The pressure difference helps propel blood through the capillary bed, through the venules, through the veins, towards the vena cava, and towards the atria of the heart. But there is so little pressure that blood pressure is normally too low to promote adequate venous return. Blood can start to get pulled down just from the pressure of gravity in the wrong direction. To help prevent blood from moving in the wrong direction, we've mentioned there are several structural differences in veins that we don't see in arteries. Like veins have a larger lumen to allow fluid to accumulate on that side. They have a thicker tunica externa so that it can help with the expansion without exploding. And they have valves to prevent blood from moving too far in the wrong direction. In addition to that, veins need some functional adaptations to help increase venous return back to the heart, like contraction of nearby skeletal muscles. As they contract, they bulge and push down on a vein, temporarily increasing pressure and pushing blood into the next portion of the vein. As the pressure decreases from the relaxation of skeletal muscles, the valve slams shut and it prevents blood from moving back down in the wrong direction. In addition to this pressure difference caused by the contraction of skeletal muscle, we also get pressure differences and changes caused by ventilation. As we inhale, it increases pressure in the thoracic cavity. As we exhale, it decreases pressure. It does a similar kind of thing for venous return as the contractions of skeletal muscles. Temporary increases in pressure push blood into the next portion of the vein. As that pressure declines, the valves slam shut and prevent blood from moving in the wrong direction. In addition to that, during times of sympathetic responses, sympathetic neural signals can stimulate the contraction of the tunica media in the veins. Even though there's very little tunica media in the veins, as it contracts, it does increase pressure and increases venous return during fight or flight responses.